In this module, we are going to learn Input-Output Matrix 2. The analysis of production and distribution of commodities and services at input-output level of the national economy was for the first time implemented in the national economy balance of the USSR in 1923-24. Professor W. Leontief, who analyzed the results of the balance research, got his article published in the journal The Planned Economy in 1936. His model was close to the scheme of the national economy balance of USSR. He implemented the idea of input-output coefficients of a single production industry for other industries, which formed the basis for the contemporary input-output model. He was awarded the Nobel Prize in 1972 in economic sciences for the development of the input-output method and for its application to important economic problems. Later in mid-90s, the input-output method became widely applicable with the upcoming use of computers. The model got improved, leading to transition from static to dynamic version, with the capital investment lag of 1 or more years forming long-term and medium-term indicative planning of national economy. As seen in our first module, the concerned question was how much should be produced by each industry of the economy so that the input requirements of all the industries as well as the final demand, as in the case of the open model, will be exactly satisfied. As discussed in detail, it was the case of a static input-output model and the mathematical formulation which led to a simultaneous system of linear equations whose solution provided for the equilibrium output levels of all the industries of the economy. However, when certain additional economic factors are incorporated into the model, the system may no longer remain a static system and can take on a dynamic character. Since the dynamic character will be in all forms dependent upon the change in time, the mathematical formulation may result in a difference or a differential equation of some particular type. Obviously, the change in time can be a continuous time change or a change occurring at some intervals over a period of time. Accordingly, time can be taken as a continuous variable or a discrete variable. In context of continuous time change, the variable xt depending on time t also experiences continuous change and therefore appears in the form of derivatives. However, in the discrete case, the pattern of change of variable xt will be described by so-called differences. Hence, in the case of continuous change in time, the mathematical model would involve differential equations, and in case of a discrete change in time, difference equations would appear. Also, based on the presence or absence of final demand, the dynamic system would be classified as closed or open. Apart from the basic assumptions as taken for the static model, the assumptions for the dynamic model would comprise of fixed coefficient production function, full utilization of the productive capacity of each sector within each period, a uniform rate of profit across sectors in each period, that is stability of long-term equilibrium. After studying this module, you shall be able to get an idea of dynamic input-output models in both its form, discrete and continuous, formulate and analyze the mathematical model for both types of dynamic models in closed and open state, determine the solution for the types of model discussed to get the output vector for the sectors of an economy. In this module, we will commence with dynamic input-output model. We begin by considering a simple economy consisting of just two sectors. In case of a static system, the variable xi represents the output of the ith industry in appropriate units. In case of a dynamic system, we will modify the notation by xit to add a time dimension to it. The notation aij will have its usual meaning of the input coefficient, that is the output of the ith industry required in the production of a unit of commodity of the jth industry. Also, DIT shall denote the final demand of output from the ith industry. Now, if we consider the open system for this static two industry economy, the output for industry I in the equilibrium case is given by x1 is equal to A11 x1 plus A12 x2 plus D1. Let us consider one period lag in the production. So the output demanded in period T determines the output of period T plus 1. Mathematically, it can be written as x1 comma T plus 1 is equal to A11 x1 comma T plus A12 x2 comma T plus D1 comma T. Similarly, for industry, the linear equation will be of the form x2 t plus 1 is equal to a21 x1 t plus a22 x2 t plus d2 t. It should be noted here that both difference equations are first order. Together they form a system of simultaneous difference equations. Now, if we represent the input coefficients in the matrix form, we get the input-output matrix. A is equal to A11, A12, A21, A22. And the demand matrix for period T is given by dt is equal to D1, T, D2, T. Let xt plus 1 equal to x1, t plus 1, x2, t plus 1 and xt is equal to x1, t, x2, t. So the system can now be written in the matrix form as x1, t plus 1, x2, t plus 1 is equal to a11, a12, a21, a22 into x1, t, x2, t plus d1, t plus d2, t or xt plus 1 is equal to axt plus dt. The system constitutes the Leontief open dynamic input-output model in discrete time lag. Generalizing the derivation for an n-sector economy, we get the same model as xt plus 1 is equal to axt plus dt, where a is equal to aij n into n and dt is equal to dit n into n and dt is equal to dit n into 1 are n squared and n column matrices respectively. Now if D is taken as zero vector, that is if there is no final demand, this becomes the case of a Leontief closed dynamic input-output model with the discrete lag given by xt plus 1 is equal to axt. Moving on to dynamic model with capital formation, as seen in static input-output model, coefficients a, I, j were taken to be non-negative, but these coefficients do not say anything about capital formation. In practice, there are other flows of outputs that are not embodied in the current output, but they serve to increase the stock of capital, both fixed and circulating. Let Bij be the stock of the output from the ith industry as the capital good that jth industry must have for each unit of its output. Now, it is possible that output from sector 1 may not be held as a stock input or say used as a capital by some other sector j. In such case, the stock coefficient or the capital coefficient Bij is equal to 0. So, the capital coefficients can be 0. However, they can be never negative. Also, as each good cannot be simultaneously an intermediate good and a capital good, so sum of Bij's and Aij's will be 0. In practice, Bij's are quite often 0. So, matrix B which is equal to Bij, though non-negative and square, it can be singular. Now, the stock of the ith good owned by the jth industry will be given by the expression Bij xj, where j is equal to 1, 2 right up till n. Clearly, this capital is always appropriate for producing the current output. Now, the variation in capital stocks, that is investment, to the output variation is given by delta xit, as the capital requirement in period t will be based on the output variation and is equal to xit minus xit minus 1. So, for each industry and n sector economy, we have the following three components. First, the quantity of output from the ith industry used as intermediate input by all industries, which is given by sigma j is equal to 1 to n aij xj comma t. Second, the quantity of output from the ith industry demanded for investment purposes by all industries, which is given by sigma j is equal to 1 to n bij delta xj t plus 1. Third, the quantity of output from the ith industry needed to meet the final demand, that is DIT. Now, at state of equilibrium, total current output of ith industry must be mathematically expressed as sigma IT is equal to sigma j varying from 1 to n aij xjt plus sigma j varying from 1 to n bij xj t plus 1 plus dit, where I varies from 1 to 2 right up to n. This in matrix notation can be written as xt is equal to axt plus b delta xt plus 1 plus dt, where xt is equal to xit into n into 1, comma delta xt plus 1, which is equal to xit plus 1 minus xit the whole into n into 1, and dt is equal to dit n into 1. This is the Leontief open dynamic input-output model with capital requirements where time lag is discrete. For dt equal to 0, the model represents the Leontief closed dynamic input-output model with capital formation in discrete time lag. Note, if the output is stationary over time, that is xi t plus 1 is equal to xi t, which goes up to xa, then the system reduces to x is equal to ax plus d, which is a Leontief open static system. Dynamic input-output model for continuous time lag. In case of a continuous time lag, the symbol xit representing the output for period t would be replaced by xit, and the variation delta xit in output would now be represented by xi prime t. So the equilibrium state of an economy is represented by xit, which is equal to sigma j is equal to 1 raised to n aij xjt plus sigma j varying from 1 to n bij x prime I t plus dit, where I varies from 1 to right up till n, or xt is equal to axt plus bx prime t plus dt, where xt is equal to xi t n into 1, xt is equal to x prime I t n into 1, dt is equal to dit n into 1, and the other symbols have their usual meanings. Or more appropriately, a minus I into t plus bx prime t minus dt, where psi denotes the n into n identity matrix. As the final demand is considered, the model represents an open dynamic input-output model with continuous time lag. To get the model for closed dynamics, we take dt equal to 0 and the model changes to xt, axt plus bx prime t. Next, we will study solutions to dynamic input-output model. Let us first consider the open dynamic model with discrete time lag. xt plus 1 minus axt is equal to dt, or xt plus 1 is equal to axt plus dt. If the initial output xo is known and the final demand for period t is specified, then the solution can be determined using the recurrence relations. Note 1. In case of a closed model, now get the homogeneous system xt plus 1 is equal to axo, for which the solution can be obtained as xt plus 1 is equal to axo if the initial output is known. For the dynamic model with discrete time lag for capital formation, the model has been formulated as xt is equal to axt plus b xt plus 1 minus xt plus dt. I minus a minus b xt is equal to bxt plus 1 plus dt.
xt is equal to I minus a minus b raised to the power of minus 1 bxt plus 1 plus I minus a minus b raised to the power of minus 1 dt, which is equal to n minus 1 bxt plus 1 plus n minus 1 dt, where n is equal to I minus in brackets a minus b. Case 1, dt is a constant. Now, if dt is a constant, maybe even 0, which would cover up the case for closed model 2, then it would be sufficient to analyze the following homogeneous system. xt is equal to n raised to the power of minus 1 bxt plus 1. Now, as I minus in brackets a minus b raised to the power of minus 1 is greater than equal to 0. If a minus b greater than equal to 0, that is if a is greater than equal to b, so n minus 1 is greater than equal to 0 if a is greater than equal to b. Also, as b is greater than equal to 0, we see that n raised to the power of minus 1b greater than equal to 0, a non-negative square matrix. Let m be equal to n raised to the power of minus 1b. So we rewrite the system as xt is equal to mxt plus 1, where m is greater than equal to 0, or as xt plus 1, which is equal to m raised to the power of minus 1 xt, which is equal to b raised to the power of minus 1 n xt. Case 2, dt is a function of t. In this case, let the initial conditions be given. Let xo and do be the initial values. The model is given by xt is equal to axt plus b in brackets xt plus 1 minus xt brackets closed plus dt, or bxt plus 1 is equal to I minus a plus b in brackets xt minus dt, or bx1 is equal to I minus a plus bxo minus do. bx1 is equal to fo, where fo is equal to I minus a plus bxo minus do is constant. Hence x1 is equal to b raised to the power of minus 1 fo. So for given xo, we get the values of x1 if b raised to the power of minus 1 exists. Again, bx2 is equal to I minus a plus bx1 minus d1. So x2 is equal to b raised to the power of minus 1 into I minus a plus bx1 minus b raised to the power of minus 1 d1.
Now, if x1 is known and capital coefficients corresponding to d1 are specified, then x2 can be determined provided b raised to the power of minus 1 exists. In other words, for given xo and dt's specified for t is equal to 0, 1, 2, right up till t minus 1, xt can be fully specified. However, by this we cannot set target values of x at time t because we cannot work out the consequence of a change in some dt. Instead, we can find by how much output at some period t is modified if consumption is changed, provided b raised to the power of minus 1 exists.
For the continuous case, the model formulated is given by xt is equal to axt plus bx prime t plus dt. The equation can be rewritten as bx prime t, which is equal to I minus a xt minus dt, or x prime t is equal to b raised to the power of minus 1 into I minus a xt minus b raised to the power of minus 1 dt, with m is equal to b raised to the power of minus 1 I minus a and n is equal to minus b raised to the power of minus 1. X prime t is equal to mxt plus n dt. For known initial output xo, using techniques to find the solution for a linear first order differential equation, we get the solution as xt is equal to emt e raised to the power of mt xo plus integration 0 to t e raised to the power of mt minus sn ds ds. Case 1, dt is equal to k, which is a constant. Then the solution becomes xt, which is equal to 1 minus a raised to the power of minus 1k plus e raised to the power of mt, bracket open, xo minus I minus a in brackets raised to the power of minus 1k, as m raised to the power of minus 1n is equal to minus I minus a raised to the power of minus 1. Case 2, if dt is equal to kt, that is final demands are steadily growing then. xt is equal to I minus a raised to the power of minus 1 kt minus m raised to the power of minus 1 I minus a raised to the power of minus 1 k plus e raised to the power of mt into xo minus m raised to the power of minus 1 into I minus a raised to the power of minus 1 k. Since by the assumptions of the model, the capital coefficients b, I, j are greater than or equal to 0, the equations represent an acceptable solution. Alternative methods to find solution of dynamic input-output model. Method of undetermined coefficients. 1. Consider a dynamic input-output model in discrete time lag for which the final demand vector is given by vector dt mu t, that is mu is a positive scalar. We use the method of undetermined coefficients to find the particular solution. We begin by trying solutions of the form x1t is equal to alpha x1 mu raised to the power of t, x2t is equal to alpha 2 mu raised to the power of t, where alpha 1 and alpha 2 are undetermined coefficients. So the output vector is given by xt is equal to alpha 1 mu t, alpha 2 mu t, which is equal to alpha 1 alpha 2 multiplied by mu t. Consider the equation for the discrete series. Xt plus 1 raised to the power of minus a xt is equal to dt, where a is equal to a11, a12, a21, a22 is the input-output matrix. As xt plus 1 is equal to alpha 1 mu raised to the power of t plus 1, alpha 2 mu raised to the power of t plus 1, which is equal to mu alpha 1 mu alpha 2 the whole into mu raised to the power of t, which is equal to mu 0 0 mu into alpha 1 alpha 2 into mu t. Substituting the value in previous equation, we get mu 0 0 mu into alpha 1 alpha 2 into mu t raised to the power of t minus a11 a12 a21 a22 into alpha 1 alpha 2 into mu raised to the power of t, which is equal to 1 1 mu raised to the power of t. As mu raised to the power of t is not equal to 0, dividing the whole equation by scalar multiplier, we get mu minus a11 minus a12 minus a21 mu minus a22 into alpha 1 alpha 2, which is equal to 1 1. Let us represent this equation in matrix form by a dash alpha, which is equal to E dash, where A dash is equal to mu minus A11 minus A12 minus A21 mu minus A22. Alpha is equal to alpha 1 alpha 2 and E dash is equal to 1 1. Now the solution to this system exists provided the coefficient matrix A dash on the left hand side is non-singular. Assuming the non-singularity of the matrix, we can find the solution by using Cramer's rule as alpha 1 is equal to mu plus a12 minus a22 divided by determinant a dash, and alpha 2 is equal to mu plus a21 minus a11 divided by determinant of a dash, where determinant a dash is equal to mu minus a11 divided by mu minus a22 minus a12 a21. Since alpha 1 and alpha 2 can be obtained in terms of the known parameters, so the particular solution can now be obtained by means of the trial solution assumed. Now for the complementary function, we consider the homogeneous system. Xt plus 1 minus axt is equal to 0. Using x1t equal to alpha 1 mu raised to the power of t and x2t is equal to alpha 2 mu raised to the power of t, we have the system as a dash alpha is equal to 0. The homogeneous system will have a non-trivial solution if determinant of a dash is equal to mu minus a11 into mu minus a22 minus a12 a21 equal to 0. That is mu squared minus bracket open a11 plus a22 into mu plus a11 a22 minus a12 a21 is equal to 0. This is a quadratic equation in mu called the characteristic equation, and its roots are called characteristic roots.
Using the values of mu in A, prime, we can determine the value of alpha 1 and alpha 2, by which we get the final form of complementary function. The general solution can now be obtained by combining the particular solution and the complementary function found. However, the general solution will have arbitrary constants which would become specific with the help of appropriate initial conditions given in context of the model.
We now consider a dynamic input-output system in continuous time adjustment. Suppose the final vector demand vector is now given as dt, which is equal to mu1 e raised to the power of rt, mu2 e raised to the power of rt is equal to mu1 mu2 e rt. Also, we assume that the input-output matrix A and the capital matrix B is given for the model where mu, I and R are constants. Again, we use the method of understanding coefficients to find the solution to this model. Mathematically, the model can be represented by the following differential equations. xt is equal to axt plus bx prime t plus dt, or x prime t is equal to b raised to the power of minus 1 minus a xt minus b raised to the power of minus 1 dt, or x prime t is equal to mxt plus n dt, where m is equal to b raised to the power of minus 1, I is minus a, and n is equal to b raised to the power of minus 1. We take the trial solution as xi is equal to alpha I e raised to the power of rt, where I is equal to 1, 2 all the way to n. Clearly, xi prime t is equal to r alpha I e raised to the power of rt. We write xt, which is equal to x1t, x2t, which is equal to alpha 1, alpha 2, e raised to the power of rt, and x prime t is x prime 1 t, x prime 2 t, which is equal to r. Alpha 1, alpha 2, e raised to the power of rt is equal to r0, 0 r, alpha 1, alpha 2, e raised to the power of rt. Now substituting the trial solution in the differential equation, we get r alpha e raised to the power of rt minus m alpha e raised to the power of rt is equal to n mu e raised to the power of rt, where alpha, which is equal to alpha 1, alpha 2, is the scalar matrix, and matrices m and n can be determined by using a and b. Now cancelling the common non-zero multiplier e raised to the power of rt, we get r1 into alpha minus m alpha, which is equal to n mu. r0, 0 r into alpha 1, alpha 2 minus m11, m12, m21, m22 into alpha 1, alpha 2 is equal to n11, n12, n21, n22 into mu1, mu2. That is r minus m11 minus m12 minus m21 r minus m22 into alpha 1, alpha 2 is equal to n11, n12, n21, n22 into mu1, mu2.
Now, the solution to this system can be obtained if the coefficient matrix on the left hand side is non-singular. The coefficients alpha I, where I is equal to 1, 2, can be obtained by using Cramer's rule. Using these value of alpha I prime in trial solution, we get the particular solution to the equation. Again, considering the homogeneous system corresponding to this differential equation, we can obtain the complementary function for this equation. Combining the complementary function and the particular solution, we get the general solution for the model, which provides the desired output vector for the open dynamic input-output model in continuous time with capital formation.
Now let us analyze some illustrations. Consider a two-sector economy whose input-output matrix is given by A is equal to 0.3, 0.4, 0.3, 0.2. Using discrete time production lag input-output model, find the particular solution of the output vector for time t, taking 0 as the base period. The final demand vector is given by the matrix dt, which is equal to 1.2 raised to the power of t and 1.2 raised to the power of t. Solution. As seen in the formulation of open dynamic input-output and in discrete time production lag, the system in matrix form can be written as xt plus 1 minus axt, which is equal to dt, where xt plus 1 is the output vector for t plus 1th period. We use the method of undetermined coefficients to solve the problem. Since dt is equal to 1.2t, 1.2 raised to the power of t. So we take xt is equal to alpha 1 1.2 raised to the power of t, alpha 2 1.2 raised to the power of t, which is equal to alpha 1 alpha 2 multiplied by 1.2 the whole raised to the power of t as the trial solution. The choice of this trial solution is based on the fact that on successive differentiation, every next expression gets a term of the type alpha into 1.2 raised to the power of t. Delta 1.2 raised to the power of t is equal to 1.2 raised to the power of t plus 1 minus 1.2 raised to the power of t, which is equal to 1.2 minus 1, the whole into 1.2 raised to the power of t, which is equal to 0.2 into 1.2 raised to the power of t. Delta squared into 1.2 raised to the power of t is equal to delta bracket open, delta of 1.2 raised to the power of t bracket close is equal to delta bracket open, again in bracket 0.2 into 1.2 raised to the power of t the whole bracket closed, which is equal to 0.2 into 1.2 raised to the power of t plus 1 minus 0.2 into 1.2 raised to the power of t, which is equal to 0.2 into 1.2 minus 1 into 1.2 raised to the power of t. This is equal to 0.2 into 0.2 into 1.2 raised to the power of t, which is equal to 0.4 into 1.2 raised to the power of t, and so on. Hence, xt plus 1 is equal to alpha 1, 1.2 raised to the power of t plus 1, alpha 2, 1.2 raised to the power of t plus 1, which is equal to alpha 1 into 1.2, alpha 2 into 1.2, the whole into 1.2 raised to the power of t, which is equal to 1.2001.2 into alpha 1 alpha 2 into 1.2 raised to the power of t. If the trial solution taken is an appropriate solution to the problem, then it must satisfy the equation of the model as given as 1.2001.2 into alpha 1 alpha 2 into 1.2 raised to the power of t minus 0.3 0.4 0.3 0.2 into alpha 1 alpha 2 into 1.2 raised to the power of t, which is equal to 1 into 1.2 raised to the power of t. Dividing the whole equation by the common scalar multiplier 1.2 raised to the power of t, which is not equal to 0, we get 1.2 minus 0.3 minus 0.4 minus 0.3, 1.2 minus 0.2 into alpha 1 alpha 2, which is equal to 1 or 0.9 minus 0.4 minus 0.31 into alpha 1 alpha 2, which is equal to 1. Solving the system, we get alpha 1 is equal to 70 by 39, alpha 2 is equal to 20 by 13, alpha 1 t is equal to alpha 1 into 1.2 raised to the power of t, which is equal to 70 divided by 39 into 1.2 raised to the power of t. X to t is equal to alpha 2 into 1.2 raised to the power of t, which is equal to 20 divided by 13 into 1.2 raised to the power of t. Therefore, the particular solution is xt 70 by 39, 20 by 13 into 1.2 raised to the power of t. Consider a two-sector economy whose input-output matrix is given by A equal to 0, half, half, 0, and the capital matrix is given by B is equal to 2, 3, 0, 0. Suppose in the third period the output desired is 200, 200. Based on this, we intend to determine the output of the first period.
Now by discrete model, we have xt is equal to axt plus b bracket open xt plus 1 minus xt plus dt. We are given x3, and from the given matrix B, it can be observed that second good is never used as a capital good, as the second row of the matrix is a row of all 0, but both the goods have the same output at the target period, that is 200 units each. So we fix the final demand of both good at the same level in the second period. Say we take D is equal to 60, 60.
Now x2 is equal to ax2 plus b in brackets x3 minus x2 bracket close plus d2, or I minus bracket open a minus b the whole into x2, which is equal to bx3 plus d2. So 3 5 by 2 minus half 1 into x1 2 x2 2 is equal to 2 3 0 0 into 200 200 plus 60 60, which is equal to 1060105, or x2 is equal to x12 x22 is equal to 4 by 13 into 99710. Now x1 is equal to ax1 plus b bracket open x2 minus x1 bracket close plus d1. Again I minus bracket open a minus b bracket close x1 is equal to bx2 plus d1. Here x2 is already known, and if the final demand for the first period is given, the output for the first period can be determined.
Now let us summarize what we have learned. 1. Input-output model that involves time-dependent output levels can be described by means of dynamic models. 2. Discrete time changes can be modeled by means of a system of difference equations, and continuous time changes by means of a system of differential equations. Mathematical model for discrete time lag is given by xt is equal to axt plus b delta xt plus 1 plus dt, where xt is equal to xit bracket closed n into 1 is the output in period t, and delta xt plus 1 is equal to xit plus 1 minus xit the whole into n into 1 is the capital requirement in period t plus 1. Fourth, mathematical model for continuous time adjustment is given by xt is equal to axt plus bx prime t plus dt, where xt is the output for period t and x prime t is the variation in output. Fifth, solutions to these systems can be found by using usual techniques to solve difference equations and differential equations.